All right, so today we're going to be going over the second part of basic principles of MRI. So just as a reminder, as a review, we talked about how our hydrogen spins outside of our magnetic field are orientated randomly. But once we put the patient inside our magnetic field, they align either with or against V sub 0. You're going to get an excess of hydrogen spins that align with B sub 0, or you could also say align parallel or spin up, and those spins have low energy. And that excess, so you add up those little vectors, and that creates our net magnetic vector. So as B sub 0 gets stronger, meaning we go from a 1.5 Tesla to a 3 Tesla, fewer of those hydrogen spins have the energy to align against. So as you go, say one of those hydrogen spins had enough energy to align against at a 1.5. But then at 3 Tesla, they just don't have that energy to align against, so they now align with. So that net magnetic vector now gets larger because you get more of an excess of those low energy spins. So if we have a larger net magnetic vector, ultimately we're going to get more signal from that patient. So that's why it's beneficial to have stronger magnets, going from a 1.5 to a 3 Tesla, because you get more signal on a 3 Tesla scanner, and ultimately you can start to adjust your parameters a little bit more. And so as you start off with more signal, then you can manipulate the parameter, get better resolution. Sometimes your scans can be a little bit quicker because you don't have to constantly add more signal. But then there are drawbacks to 3 Tesla scanners because they tend to heat up the patient a little bit more. So we'll talk about that in future lectures. So this is just another diagram because this is a good introduction to what we're going to talk about today, because we've talked about this net spin. So this spin right here is what we've discussed so far. And that comes from the 1 proton in the nucleus, but 0 neutrons. So that neutron, if there's no neutron to counteract that proton spin, you get net spin. Or they sometimes call it angular momentum, right? So we have net spin. But then when you're talking about another external magnetic field, there's going to be another type of spin that gets factored in. We're going to talk about it today, but it's called precession. Okay, it's called our secondary spin. So you have net spin, but then the hydrogen proton also spins around B sub 0 at a certain frequency and along a certain precessional path. So just put it right here next to this little arrow, net spin, angular momentum, and then around this circle right here, put precession. Okay? But then once again, this is showing the relationship of high to low energy spins. We always get an excess of low energy spins, and in this example, we just have one excess of low energy spins, but that creates our net magnetic vector. Right? Just a review of our coordinate system in our 3 orthogonal planes. So we have to really start thinking 3-dimensionally in MRI, right? So in X-ray, we're dealing with just 2 dimensions. You had an AP. You had a sagittal, right to left. You had a coronal. I already said AP. But then you could do like an axial of the shoulder, which is going superior to inferior. It's really only 2 dimensions. But now we have the ability to see things in the 3 orthogonal planes and the possibility of actually seeing things in oblique planes. So let's just review this. So this is our coordinate system. So we've talked about B sub 0. So the longitudinal axis runs parallel with B sub 0. Okay? Our XY axis is what we call the transverse plane. And that transverse plane is 90 degrees to our longitudinal axis. And just think about our x-axis coming out towards us. It's hard to draw a 3-dimensional diagram in 2D, but imagine this one's coming out towards us, and then this one's shooting off to the left and to the right. Okay? Any questions about our coordinate system? All right, so getting to precession. So the book definition is the secondary spin of magnetic moments around B sub 0. Or sometimes it's even simply described as a wobble of magnetic moments around B sub 0. So once again, this little arrow is denoting our net spin or angular momentum. And then this path and this spin around this B sub 0 axis, so if you want to further label this diagram, put B sub 0 right here, you have this secondary spin around it, and that's called precession. Okay?
So would you describe like net spin as like the Earth rotating on its own axis, and then precession is the Earth rotating around the sun?
Yeah. Another good example, and we'll get to it here, is talking about how you have like a spinning dreidel, and you spin it, that's your net spin, but then Earth's gravitational force, that's another, you think of it as a magnetic field, because it really is, but as that dreidel starts to slow down, right, it starts to wobble. So it's just a secondary spin when you have a charged particle in motion around a magnetic field. But yes, you could say that for sure, having like an orbit around something that's already spinning on its axis, for sure. But I would think of almost that as like an electron spinning in like its orbital shells, you know what I mean? So maybe just a little bit different. Okay, so another way to describe precession. So this is a spin is a tumbling motion through space that MR-active nuclei possess without the presence of an external magnetic field. So that's net spin. So the influence of an external field, B sub 0, will cause that secondary spin. And once again, that's precession. So we have two spins. And here is that example of that dreidel. You have it spinning on its own axis. But then when gravity starts to take over that spin, it creates that wobble before gravity fully takes over, and then it just drops to the ground. Okay? So we have the same kind of concept going on here, where we have the net spin of the hydrogen proton or protium, and then you get precession around B sub 0. All right, so let's define a couple things dealing with precession. We have the precessional path, and that's denoted by the dotted line up here. And that's the circular path that the magnetic moments follow around B sub 0. And then the precessional frequency. That's the speed at which the magnetic moments are precessing around B sub 0. So how fast they're spinning around B sub 0. And that's usually measured in megahertz. Okay? So do you remember our standard frequency when we were talking about frequency and wavelength and our sine waves? What was our standard frequency? Well, the units is hertz, but what was our standard frequency that we usually deal with? I mean, they can be at different ranges, hence the megahertz. But what is considered standard frequency? 60 hertz. Remember, standard frequency was considered 60 hertz? And that really just broke down to 60 cycles per second. But if we just have 1 hertz, that's just 1 cycle per second. Okay? But when we talk about megahertz, we're really getting into the hundredths of thousands cycles per second. So this precessional frequency is directly affected by the external field strength. So you'll see how that factors in. Our precessional frequency is influenced by B sub 0. And that makes sense because that's the axis that it's rotating around. So the influence of B sub 0 produces additional spin or wobble of the magnetic moments. The additional spin is called precession. Precession causes those magnetic moments to follow a circular path around B sub 0. That's called the precessional path. The speed at which they wobble is the precessional frequency, and the unit of precessional frequency is in megahertz. You guys still with me so far? Okay. All right, so the most important equation in MRI. So put a little star next to it. It's our Larmor equation. So to determine this precessional frequency that I keep talking about, or it's also referred to as the Larmor frequency, you use the Larmor equation to calculate that. And so the equation goes W sub 0, which stands for precessional frequency, and the unit is in megahertz, is equal to B sub 0, which is in units of what? It's not on here, but what is it? What strength is the magnetic field that we deal with in MRI? Tesla. So it's units of Tesla. And we multiply that by our gyromagnetic ratio, which is a constant for each MR-active nuclei, depending on which one you're trying to image. And we're going to be focusing on, once again, hydrogen. And I'll give you the unit here in a little bit. But please put a star next to this, because this is the most important equation thus far, but it is probably the most talked about equation in MRI. So here's just another way that they can write it. Sometimes they denote it by a little f equal to our gyromagnetic ratio times B sub 0. So we've talked about precessional frequency and its unit. We've talked about B sub 0 and its unit. So the only thing that we really haven't discussed is this gyromagnetic ratio, what it is and how it factors into this equation. So the gyromagnetic ratio expresses the relationship of the nuclear spin, remember, also called angular momentum, and the magnetic moment of each nucleus within the external field. So each different MR-active nuclei have different gyromagnetic ratios. So remember, we talked about a bunch of MR-active nuclei. We talked about hydrogen, but we also discussed various others like oxygen and carbon. And what did they all have in common? What was their Z number? What was their atomic number? Was it odd or even? It was odd, right? And that makes sense because you have typically more protons inside the nucleus than neutrons, and that gives it net spin. And anything that has net spin creates a small little magnetic field around it. So we can image those things in MRI, but why do we typically not image carbon and oxygen? What's the issue with it?
They're not as abundantly found in the body.
They're not as abundant and found in the body as hydrogen. Good. So the gyromagnetic ratio for each MR-active nuclei is a constant. And it's expressed as the precessional frequency of that particular nuclei at 1 Tesla. Okay? So the unit of the gyromagnetic ratio, sometimes it's denoted as lambda, is measured in megahertz per Tesla. And that makes sense because, remember, B sub 0 units was Tesla. And so if this is megahertz per Tesla, we cancel out that Tesla, and all we're left with is megahertz for our precessional frequency. So this is a constant, and you need to remember this number by heart. So the gyromagnetic ratio of hydrogen at 1 Tesla is 42.58 megahertz per Tesla. So you can round that up to, sometimes you'll see it in the book as 42.6, but make sure you know that number by heart. And remember, that's at 1 Tesla. So I have different field strengths, and what I want you to do is calculate the precessional frequency of each. All right. So first one, 0.5 times this number. What did you guys get?
You got my pencil out.
I heard 21.29. Good. All right. 1.5 times 42.58.
63.87.
Good. 63.87. 3 Tesla times this number. 127.74. And then the last one, 5 Tesla times the gyromagnetic ratio of hydrogen.
212.9.
Good. So it's on the next slide. So you guys can see that this is a linear relationship. So see, as we increase our magnetic field, so does our precessional frequency in a linear fashion. Okay? So if you're going to highlight certain values here, obviously you need to know the gyromagnetic ratio. But if you want to remember 63.86 or 127.68, that's important because we really just deal with 1.5 Teslas and 3 Teslas within the MRI system. Okay? So this will factor in when we talk about making sure we fat set appropriately and various other things dealing with our precessional frequency. Good. So this is just a kind of a note that we still do have other MR-active nuclei that have a certain gyromagnetic ratio that is a constant at 1 Tesla. So you can see here with carbon, the gyromagnetic ratio is 10.7, nitrogen 4.3, and oxygen 5.7. So with that being said, it also creates, when you plug in those numbers to the Larmor equation, you also create different precessional frequencies, which are also called Larmor frequencies, so don't get that confused. So when we talk about the next concept, it's called resonance, where we're applying a radio frequency at a very specific frequency, and it's usually in the range of our precessional frequency of hydrogen. We're just going to excite hydrogen nuclei. We're going to ignore all these other elements. And that's important because we just want to look at hydrogen and the tissues that are incorporated with hydrogen. Okay? So that's a very important concept when we talk about resonance, which is on our next slide, where we apply an external radio frequency at a very tuned, specific rate, which is at the rate of precessional frequency of hydrogen. We're able to excite those spins, and we can flip them into our transverse plane and really image those tissues specifically. All right. So the next major concept in this unit is resonance. So the first one was precession. We got a good understanding of that. The next one is resonance, and hence where we get the term MRI, right? Magnetic resonance imaging. So obviously it's a very important concept that we need to know. So resonance, this is a phenomenon that occurs when an object, and the object here is our hydrogen net spin, hydrogen protium, is exposed to an oscillating, or you could also thinking about it's not a static magnetic field, it's a moving magnetic field, or also an RF pulse, you can think of it, or sine wave, right? And that is denoted by B sub 1. Because now this is our secondary magnetic field that we're dealing with. And this oscillating RF pulse that has a frequency close to its own natural frequency of oscillation. And what we're talking about, its own, it's that hydrogen spin. So this RF pulse is going to be applied close, and we usually give a range because it can vary just a little bit, at the precessional frequency of hydrogen. And when this nucleus is exposed, and the nucleus, once again, hydrogen, to this external force that is oscillating similar to its own frequency, the nucleus will gain energy from that external force. So we're almost putting energy into the patient, energy into those hydrogen spins. Remember, and they were low energy to start with, right? Because they're all those low energy spins that add up to the net magnetic vector. So they're already starting off low energy. We're putting energy in, and that energy will ultimately, given those spins, the ability to oppose B sub 0 and flip down into the transverse plane. So here is a YouTube video that is a good example of how the concept of resonance is kind of applied and it works. So we have, in this video, 2 tuning forks. And then the first example, I believe, they're set at different tunes. You have like a tuning fork that's a C note and a D note. And when this person knocks on one, and if they're not tuned to the same frequency, and they're put close to each other, they're not actually touching, the other one doesn't make a noise. But when you have 2 tuning forks that have the same tune or pitch, if you knock one on the left, you can bring the other one close by and not actually even touch, and it will cause that one to resonate. So it's pretty cool. So let's watch the video. So what's going on there is really, when you hit that tuning fork, they're not touching, but those RF waves are resonating at the same frequency, and that other tuning fork will start to vibrate. And that's called an efficient exchange of energy in that scenario. All right, so let's talk about this B sub 1, this radio frequency pulse that we're applying. So this is a medium used to transfer energy at the exact precessional frequency of hydrogen. It's delivered at the exact Larmor frequency of hydrogen with the result of resonance. And resonance is really just an efficient transfer of energy from one medium to another. Here it says other MR-active nuclei, like carbon and oxygen, may have a line with B sub 0, but they're not going to gain energy as their precessional frequencies and gyromagnetic ratios are different. So once again, we're ignoring those other MR-active nuclei. So let's further describe B sub 1. This is an oscillating magnetic field, so it's not static. Remember, B sub 0 is a static magnetic field. This one's oscillating, it's changing constantly. That causes a phenomenon called resonance. And remember, these can be mapped on our electromagnetic spectrum. And what ultimately is going on, we have a magnetic field and an electric field moving in space together at what? 90 degrees or parallel to each other, those two fields. 90 degrees. Yes, the magnetic field and the electrical field are moving through space together at 90 degrees from one another. So this RF pulse actually has a magnitude several orders lower than B sub 0, so it's usually in the range of millitesla as opposed to Tesla. And remember, you're dealing really with our radio waves. So you can see here that we're in the range of megahertz for our radio waves. So MRI is in this range, but we know our ionizing radiation is way up here in our electromagnetic spectrum, meaning it has a higher frequency and a shorter wavelength, which causes the ionization of atoms. So, in summary, if we deliver an RF pulse at the specific precessional frequency, the matter or the tissues will absorb energy from the RF pulse and resonate. If the RF pulse is delivered at different frequency than that of the Larmor frequency, resonance will not occur. And then the application of the RF pulse that causes resonance to occur, we have a specific name for that pulse. It's called our RF excitation pulse, because we're exciting those tissues by putting more energy into them. So that's where it gets its name. It's RF excitation pulse. And we describe that when we talk about pulse sequences, kind of the first pulse that we apply in our pulse sequence. But we're exciting those tissues, giving them energy. So with excitation, you get the absorption of energy. This will increase the number of spin-down hydrogen nuclei, because here they were low energy, but you apply that RF pulse at 90 degrees, B sub 1, to these hydrogen spins. This is B sub 1. Now there's energy in these low energy spins. And that excess energy will allow them to now start to oppose B sub 0. So they go from low energy to now they've gained enough energy to join the high energy population. Okay? So that vector, that net magnetic vector that was aligned with B sub 0, you guys start to see that it's going to start to oppose B sub 0 with this excitation pulse. So we have a couple results of resonance. Two major things happen. So the two things that happen when we turn on an RF pulse, or you could even add in another word, RF excitation pulse. And remember, it has to be at the Larmor frequency of hydrogen. First, the net magnetic vector, which was aligned with B sub 0, moves out of alignment. So here's a good diagram of that. Here's the net magnetic vector. It was parallel at the moment with B sub 0. We apply that RF pulse, B sub 1, and now you put energy into those low energy spins. They gain enough energy to oppose B sub 0. And that's so important, right? Because where do we collect that signal? On that transverse plane. Okay? But at the same time, as the net magnetic vector moves out of alignment, all the little spins all those little hydrogen spins, they start to precess in phase. So remember, this was our precessional path around B sub 0. So let's kind of add to this diagram. So remember, B sub 0 ran straight up and down. And that precessional path was denoted by that dotted line. But that's that secondary spin. But what it means by they're in phase with each other, that means that they're at the same point along that precessional path. They're at the same point along that precessional path. They're in phase with each other. Okay. So the subsequent slides are really going to start to go over these two concepts. So further on how the net magnetic vector moves out of alignment. So once again, resonance will cause the net magnetic vector, which is now denoted in purple, to no longer be parallel with B sub 0, but at an angle with B sub 0. Okay? And in this drawing, it just happens to be at 90 degrees. But that's not always the case. We'll get to what this angle is here in a moment, but that's our flip angle. And 90 degrees is usually how they draw it initially, because that makes the most sense, because that really gives us our most signal when we flip it into 90 degrees into that transverse plane where that coil, that receiving coil is. But based on the pulse sequence that we choose, a gradient echo or spin echo, the flip angle will vary. And we'll go over that when we start to cover pulse sequences. But right now, we're just going to kind of choose the simplest flip angle to make sense of this phenomenon. Okay? So the angle at which the net magnetic vector moves out of alignment is described as the flip angle. So here is the flip angle. So let's talk about that flip angle. So the flip angle, the magnitude, or you could say the degree of the flip angle. So you could say magnitude, but the degree depends on two things. The amplitude of that RF pulse, the amplitude of B sub 1, the amplitude of B sub 1, and the duration. Or you could say the amount of time. Put next to duration, amount of time the RF pulse is applied. Now remember, we have to have it tuned to a certain frequency, right? But amplitude just means how high and low those peaks are. But it's still at the precessional frequency of hydrogen. It's still at the precessional frequency of hydrogen. But the amplitude is just how high those peaks go. And then the duration is just simply how long we apply it for. Okay? So that's always a registry question. What are the two things that determine flip angle? Amplitude and duration of RF pulse, which is B sub 1. So the flip angle in the most simple context is usually at 90 degrees. Because once again, at 90 degrees, that's our transverse plane. Our net magnetic vector is rotating around it now. And we're getting good signal coming from our patient. But you'll see as you start to learn more about MRI, that angle can vary. It can be less than 90, it can be more than 90, depending on the pulse sequence that we're creating. All right? So let's talk about that coordinate system once again. So M sub z, that's our longitudinal plane. And is that parallel or perpendicular to B sub 0? What do we think? Parallel or perpendicular to B sub 0? From our previous diagrams on other slides, you might see it's parallel to B sub 0. The longitudinal plane is parallel to B sub 0. And M sub z can also be denoted as M sub 0. Remember our initial magnetization plane. So these are just concepts that constantly sometimes get interchanged in questions. So that's why I want you to really kind of hit these things home. So it's not like they're trying to be tricky. It's just they like to have several names for these coordinate systems, your magnetic vectors, because you can use them interchangeably. All right, and then let's talk about our plane now 90 degrees to M sub z, which is our transverse plane. And we know now that that is perpendicular to B sub 0. All right, so here's just a diagram of the first result of resonance. And remember, that was really just the concept of giving energy to this vector, has now enough energy to oppose B sub 0, and it flips down into the transverse plane. And here it's slowly flipping down into the transverse plane. And depending on the amplitude and duration, we get a certain flip angle. Okay? So at 90 degrees, you can see the entire vector flipped into our transverse plane. But imagine if we only applied a certain duration a little bit less, or an amplitude a little bit less than this example, and it only goes 45 degrees. And when that happens, remember we talked about how oblique vectors can be broken down into smaller vectors on our orthogonal planes. And what happens is the entire vector doesn't go into the transverse plane, only a portion of it. And then a portion actually stays in the longitudinal plane. So of these two examples, which one do you think will produce more signal? 45 degrees or the 90 degrees? What do you think? And why? What's larger in rotating around that transverse axis in the 90 degrees? This, the net magnetic vector. Remember, that's your signal. So if we have a larger vector in the transverse plane, by flipping the entire thing down, that larger vector is rotating around that coil. It's a larger magnetic field, which will create a larger current going through that coil through Faraday's law of induction, right? So just don't get confused by how the vector here is kind of at 45. I was just trying to show you that it's going down completely. Here, just imagine this vector just stopped right here. Okay? You guys get that?
I think you lost me.
Okay, so back to just my diagram, I was saying see how the vector started up here, and then I was just trying to show its progression going all the way down, and then it's completely in the transverse plane for the 90 degrees. But then for the 45, just imagine the vector started here and then just stopped right at 45, and it creates these two smaller vectors. Okay, so up to this point, just know what a flip angle is, how the degree is created, the amplitude and duration, and what happens in terms of a larger or smaller net magnetic vector in the transverse plane. But ultimately, a larger net magnetic vector in the transverse plane creates more signal because you have a rotating magnetic field that's larger around a coil that's on the patient's body. So here's another way that it's just shown in a three-dimensional diagram, but it's no different. This vector flips into the transverse plane, and due to precession, remember it's precessing around B sub 0, it's just going to keep rotating around on that transverse plane. These receiving coils are stationary, right? But due to Faraday's law of induction, if we have a rotating magnetic field around a stationary coil, you're going to create, an electromotor force in that coil, a voltage. A current will start to flow, those electrons will start to flow in that coil. And that coil is connected to our system, our computer. So all that signal will be sent to our computer, and ultimately that's how our images are created. Very simplified version of it. So here is once again another three-dimensional view of that vector on the transverse plane rotating around its axis. We have a stationary coil, and due to Faraday's law of induction, we create a current, and a current is induced in the receiving coil. This is a diagram if we looked at the top, right? Imagine we are looking right down at B sub 0, or the longitudinal axis is coming at us. So let's label that. That's our longitudinal axis coming right at us, M sub Z. And this right here is our transverse axis going around. So it just wants to show you how it rotates around it 360 degrees. And that makes sense, right? These sine waves are applied in a sine wave fashion, which is 360 degrees. And ultimately, the voltage sent to our computer system is the signal that we're going to get on our MR image. All right, so that really wrapped up just that first thing that happened as a result of resonance. The net magnetic vector opposed B sub 0. The angle at which it opposes is called the flip angle. It rotates around the transverse axis and creates signal by inducing a current in the receiving coil. So the second result of resonance, let's get back to it. So now the hydrogen, once again, are moving in phase with each other. So what does that mean? They're in the same position of the magnetic moment on precessional path around B sub 0 at any given time. You have several terms for in phase, and the other one is called coherent. So if they're in phase with each other, if these spins are in phase with each other, it's called coherent. If the magnetic moments are not on the same precessional path, they are considered out of phase or incoherent. So just make that relationship. Out of phase, incoherent, in phase, coherent. And remember, when resonance occurs, all the magnetic moments move to the same position on the precessional path and are therefore in phase with one another. So when the spins are precessing in phase, they are all at the same location within their precessional path. The effect is additive and produces a strong signal in the receiving coil. So think of these as the individual little vectors that add up to be the net magnetic vector, right? All the little individual vectors that add up to be the net magnetic. And they happen to be at the same spot along that precessional path. And when that gets flipped into the transverse plane, it creates a very strong signal. Okay? This is what we want. We want strong signal being collected by a receiving coil. Right? But we can't keep that RF pulse on the entire time. We actually have to turn it off to allow those tissues to start to relax. That's another major concept we'll get to next unit, relaxation. And the relaxation is beneficial because tissues relax at different rates. So we start to get the contrast between our tissues. So when we turn off that RF pulse, our spins are no longer going to be in phase with each other. Okay? They're going to be out of phase, or also called what? Incoherent. They're going to be incoherent. They're out of phase. And when we have spins at different phases, we start to get what we call this free induction decay. Our tissues start to decay. Our signal starts to decay, meaning it starts to go down. So as we turn off that RF pulse, our spins now are going to be incoherent. And if we have spins that are next to each other that are different phases, our signal starts to decay, and it decays very rapidly, like in the order of milliseconds. You can see how we had that receiving coil, and we were getting good signal, but the moment we turned it off, if you draw a slope on top of this right here, our signal starts to decay rapidly. Okay? And this is described as the free induction decay. And its acronym is FID. So make sure you know this concept, FID. Once again, when the RF excitation pulse is switched off, this is just a reminder, any system will drive to its lowest possible energy state. So remember, we put energy into these spins so that they could oppose V sub 0. So now they're at a high energy state, right? Which is good because we're getting good signal. But the moment we turn off that RF pulse, which was adding energy into those hydrogen spins, they're going to dephase and go out of phase with each other. But also, what do you think is going to happen to that net magnetic vector that's in the transverse plane? Where do you think it's ultimately going to go back to?
The longitudinal plane.
The longitude. It starts to realign with the longitudinal plane. And it starts to relax. That's what we call it. A process in which these hydrogen spins lose that energy. And ultimately, how we get contrast in our MR images is that body tissues relax at different rates. Muscle relaxes at a different rate than fat. Fat relaxes at a different rate than CSF. So, as long as we apply a certain TR and a certain TE, we can really highlight the differences in those tissues. So we'll talk about how we set our parameters to get good contrast on our image. But ultimately, relaxation is contrast on an MRI image. So as relaxation recurs, that net magnetic vector, which was in the transverse plane, realigns with B sub 0. Because the high energy nuclei, which were also called the spin down, return to a low energy state. And so this is actually how we get this diagram, this free induction decay. Look at it. Remember, it's rotating along that transverse axis, so as it realigns, it just kind of starts to loop up, loop up, loop up, loop up, back to B sub 0, because you still have that secondary spin called precession. So it kind of realigns in this kind of wonky fashion right back up, B sub 0. And if you just turn this little diagram on its side, see how it kind of correlates to our free induction decay. Okay? So any questions? What are the two major things that happen during resonance? What are the two major things that happen during resonance? Okay, that's a good way to say it. It aligns with the transverse. Let's rephrase it a little bit. It goes out of alignment with the longitudinal plane. That might be a better way to say it. So it gains enough energy to go out of alignment with B sub 0. And yes, it does go in the transverse plane, but not always exactly in the transverse plane. So that's, when we talk about flip angle, it's not always going to be exactly 90 degrees. But yes, it does allow enough energy to oppose B sub 0. Okay, that's the first thing. What was the other thing that happens during resonance?
The spins become coherent.
Spins become coherent. And when spins are coherent, that produces the largest amount of signal in our receiving coils. Because they're happy when they're coherent. and they're next to each other. We have hydrogen spins all throughout our body, and they're next to each other. So if they're in phase with each other, they're not going to cause what we call free induction decay or rapid decay. But if they're out of phase with each other, that signal starts to rapidly decline. Okay? So good.